Welcome to Monday morning. Yeah. Yeah, we're all trying to get used to this schedule again. Okay, what we're going to do is we're going to finish up Chapter 1, and then we're going to do Chapter 2 today. So we were just on the tail end of Chapter 1. We just had a couple things that we needed to clarify. Okay. All right, we talked about variables and characteristics of variables. We talked about levels of measurement or scales of measurement. Right? I know you guys are saying, like, that was Wednesday. Does she expect me to remember anything today? Wednesday. Okay, so let's finish up. So what we were up to was a distinction between parametric and non-parametric statistics. Now, in this class, you're going to be doing, like 99% of what we're going to be doing in this class is what's called parametric statistics. First of all, let's see if we remember. What's a parameter? What's a parameter? Yeah. Yeah, it's a number calculated or measured from an entire population, right? As opposed to what? A statistic, right? A statistic is from a sample. So a parameter refers to numbers calculated or measured from a population. So there's an entire branch of statistics called parametric statistics, which involves parameters and the distributions of their parameters. Okay? Right, a distribution is like a listing of scores. Okay, so parameters and their distributions. So that's mostly what we're going to be dealing with. Now, mostly parametric statistics are done with interval and ratio data. In theory, right, interval and ratio level data. Anybody remember what was interval and ratio level data? Right, scales of measurements. Interval level. What was interval level or an interval scale? Yeah. Yeah, right. Differences between adjacent values, the intervals are the same. And what was the only distinction with ratio? What did ratio have that was different? Yeah? Yeah, it's a true 0 point, right? A true 0 point meaning you could have a 0 in the scales. Like Celsius had a 0. But 0 in a ratio scale means the absence of the characteristic. The absence of the characteristic. So parametric statistics really should be done on interval and ratio level data. However, I'll tell you right now, there are times that we do parametric statistics with ordinal level data, right? Ordinal level data are things are in order, but the intervals are not necessarily equal. It's one of those weird things. One of the things that you're going to find, especially for those of you who are going to do any kind of research, you need to find out what's typically done in your discipline. Because sometimes things are allowed within your discipline that might not be allowed within another discipline, right? Okay, it really depends on the variable. Okay, so parametric statistics, in theory, you need interval or ratio level data. Also, every test that we're going to learn from here on in has what we call assumptions that go with it. Assumptions, certain things that we have to meet, right? When you meet an assumption, like you're coming to class, you're assuming that it's going to be always in this room, right? That's an assumption. So all the tests that we're going to be looking at, you have to meet certain assumptions. Sometimes we violate those assumptions. Sometimes our data does not live up to those assumptions. It happens, especially when you're dealing with real-world things and people. It's messy, okay? So when you violate those assumptions, then you also cannot do parametric statistics. Okay? Then you also cannot do parametric statistics. So then we have another branch called non-parametric statistics, which is entirely other, right? It avoids those problems. But for this class, for the entire semester, we're going to be doing parametric statistics up until the very last chapter. The last chapter is the only chapter we're going to be doing non-parametric statistics. Okay? Which is interesting because non-parametric statistics are used for a lot of things that affect your life really directly. Every time a telemarketer calls you and says, hello, do you use Gleam toothpaste? Or how do you feel about the war in Iraq? Or are you in favor of gun control? Those kinds of questions, right? How do you answer those questions? Yes, no, maybe, right? All things like that. Well, those are First of all, anybody guess what level of data measurement is that? Scale of measurements. Something like if I ask you, are you in favor of the war in Iraq? And the question is answered yes or no. So what is it? I heard somebody say it. Nominal, right? Nominal level data. So you're not going to do parametric statistics on that. Good. Right? You're not going to do parametric statistics on that. You're going to do non-parametric statistics with that. Okay? But things like that we hear all the time. But usually they're given short shrift in this kind of a stat class. But you know, we'll get a flavor for them towards the end. So that's the difference between parametric and non-parametric statistics. And the last thing here, experimental versus correlational research. Often, we're doing studies on groups that are already pre-existing. For example, gender differences, boys versus girls, you know. I don't have like a group of kids and say, okay, I'm going to assign you to be a boy and you to be a girl, right? That doesn't happen. They're already pre-existing. Now, when you're doing analysis with pre-existing groups, it's a different paradigm than when you're doing it experimentally. In an experimental paradigm, I can assign people to a group. Right? Like I decide one group stays in the red room and one group stays in the blue room. Okay? That's under my control. Whereas if I'm doing a difference between boys and girls, that's not within my control. Okay? So in correlational research, we can talk about finding relationships, but you cannot determine causality. Right? Correlation does not imply causation. The analysis can be exactly the same, but the interpretation of your results is different. So for example, here's an example. If we're looking at the relationship, and I knew there was something I wanted to do, the relationship between paternal unemployment and child abuse, okay? There is a relationship between paternal unemployment and child abuse, but that does not mean that the unemployment causes the child abuse. What could be another alternative? What could also be an alternative? Can anybody think? Yeah. Oh, that's interesting, right? That maybe that the abuse is causing the unemployment in some way, right? Yeah. Right, okay? There might be a third factor involved that's confounding the relationship. She mentioned something like substance abuse. What about paternal aggression, right? If somebody scores high in an aggressive scale, they might have trouble holding down a job, and they might be abusive. Right? So you might find this relationship, but you cannot prove causation. Also, I mean, you know, smoking and cancer, the original studies looking at smoking and cancer were correlational. Right? We found relationships between people smoking and who got cancer. You can't do that experimentally with people. You can't say, okay, we're going to take a group of people. You guys smoke, you guys don't smoke, and we'll see who develops cancer. Right? That's not ethical. So, but originally we found correlations, we found relationships. And then animal studies started being done, and then you could get closer towards causation. But so you need to understand that. Okay? So that distinction. All right, any questions on that stuff? That's pretty straightforward. Yeah, go ahead. Yeah. Ordinal level data, parametric or non-parametric. Well, again, what I was trying to make clear there is that theoretically, really you should use non-parametric stats to analyze it. In practice, sometimes people use parametric stats to do it. As a matter of fact, we will be doing that. IQ, right? We mentioned that IQ is actually we can think of it as ordinal level, but we will be using parametric stats to analyze it. Okay? Anything else? Okay, good. So what we're going to do really quickly, because I think all of you probably will get a grip on this very quickly, is some basic summation notation. And this is the kind of notation that we use in statistics. And we'll just start with a really simple thing, and then I'll talk about a couple of rules. So let's look up here at the top, eh? Greek letter? What is it? Sigma, yeah, a big Greek letter, sigma. By the way, we're going to see a small sigma. This is a big sigma. Okay? And it means sum of, right? Sum, add it up. Add it up. So in its like simplest form here, what we have here is x is our variable. The letter x is representing a variable. Okay? I, at the bottom here, I is an index. And it tells us which scores we're paying attention to. Now, sometimes we need to be paying a lot of attention to that. In this class, because it's so basic, generally we'll actually drop the index because generally we will be looking at all the scores. All the scores. Okay? So I equals 1 means start with the first score. We're going to add up these data, start with the first score, and go all the way to the top, which has n. What does n stand for? Sample size. Sample size. So what that little notation is saying is add up all my x scores, starting with the first score, going all the way to the last score. Like I said, I'll wind up dropping the notation, those the indices, that one and that one, because we're going to be doing all the numbers. But you can, just get a glimpse into what this is. So let's just do some basic examples. All right? Here's x. I have 3 scores for x, which means that n equals 3, yeah. That's going to be a big question all semesters. What is n? Okay, and we have y scores. We also have 3 y scores here. So we have 2 variables. Okay? So let's just find the basics here. So for example, what's my sum of x? 10, good. Right? It just means add up all my x scores. For that matter, let's get the sum of y while we're here. What is it? 11, good. Okay, let's move on to this one. The sum of x squared. What does that mean? That means take each x score, square it, and then add it up. Right? Take each x score, square it, and add it up. So you could actually do this pretty easily. Anybody have this one? 38, yeah, good. Okay. And that one, that notation is different from that one because that last one says, the sum, did you have a question? Oh, the sum of x in parentheses squared. So that one says, get my sum of x and then square it. You're going to see these 2 notations all the time, so get used to that. So if we do that, what is that? Yeah, 100. Okay. Now let's talk about some really fast rules dealing with summation notation. Okay? This first rule, right? The sum of x plus y. The way it says here on the left really says add the first x score with the first y score. And then add the second x score with the second y score and the third x score with the third y score. Add those all up, right? The simpler way of thinking about it is this. It's just simply equal to the sum of x plus the sum of y. That's it. Do the numbers. Do the numbers, right? Because what this is saying, I'm seeing people with quizzical looks on their faces, right? 3 plus 4 plus 2 plus 1 plus 5 plus 6, right? That's what this is. That's what it's saying. But it's much simpler to add up the sum of x plus the sum of y, right? Which equals 21. Good. Okay? And so this second one is the same thing, but it's just subtraction. I'm not even going to do an example. They're just easier ways of writing these things out. Second summation rule here. The sum of c, what's c going to stand for? A constant, right? A number that doesn't change. So let's make, what are we going to make? C, we're going to say is equal to 7. Now, how many x scores did I have? 3, right? So in this example, my n equals 3. So that would mean the sum of c, adding c 3 times, right? The easier way to do it is just n times c. right? It's the same thing. Instead of going 7 plus 7 plus 7, you're saying 3 times 7 is 21. Okay. Third summation rule. The sum of C times X. With that on the left, what it's saying is take your constant, multiply it by the first X score. Take your constant, multiply it by the second X score. Take your constant, multiply it by the third X score, and then add those up. It's much easier to take the constant outside and just say it's C times the sum of X. Much easier. So in this case, what do we have? Our C is 7. What was our sum of X? What was our sum of X? 10, yeah. Okay. And then the last rule here is simply that the sum of xy, what would that be? x1 times y1 plus x2 times y2 plus x3 times y3. That's all that this is saying. It is not equal to the sum of x times the sum of y. Okay? Because if we were doing this, what would this be over here? Well, let's see. It would be 3 times 4 plus 2 times 1 plus 5 times 6 equals what? It's just to keep you on your toes because it's 9:30 on a Monday morning. 44, good. Right, that equals 44. What is the sum of x times the sum of y? What was that equal to? Right, that was 10 times 11. Yeah, 110. Okay, so those two things are not equal to each other. Very simple, basic rules. Okay, questions on that? Yeah. Mm-hmm. Well, no, yeah, it's a rule. It's a rule. She's just asking, like, well, what do I do on an exam, right? It's just a rule so that if you saw something that looked like this, don't think you can solve it by doing that. Okay? All right? And then that last little thing there, that last little throwaway note I have there, rounding off numbers. People always come to me and say, what do you want me to round off to? First of all, you should read the section in the book, but I'm not going to belabor the point too much. But this is the rule I want you to follow, okay? When you're doing intermediate calculations, right? Because invariably when you're doing a problem, it's not just one step, right? There's several steps. The intermediate calculations, you should carry your decimal places to 4 places. 4 places. Your final answer should be rounded off to 2. Your final answer should be rounded off to 2 places. 2 places past the original data, really. Yeah. That's fine. You don't have to do it to 4. It's just some people are better with their calculators than others. So, you know, the more the better. Why do you have to carry it to so many decimal places? What's the problem? Anybody know what the term is called? Yeah. Yeah. Yeah, rounding errors. Rounding errors. They can be really serious, especially if you have many steps and you round off. By the time you get to the end, your number may bear some resemblance to what it should be, but it'll look off. It'll look wrong if you have too many rounding errors in there. Okay? All right, that's chapter 1. So let's be done with that. Okay. Before we get started in chapter 2, I have something to tell you about. This is a Census Bureau report from 1994. Okay? So just listen up for a minute. And this is It's on number of peoples and families, okay? Household and family characteristics, that's the report, found that there were, and this was 1994, okay, found that there were almost 25.1 million married couples with children, an increase of over 500,000 from the 1990 level, and close to the 1970 peak of 25.5 million. Okay, y'all got that? All right, just going to read it one more time. Found that there were almost 25.1 million married couples with children, an increase of over 500,000 from the 1990 level. But those are the key parts. Okay? Now, how was this reported? And again, so this is like out there for the journalism students and for people who are reading, you know, which should be all of you, but we're going to reserve judgment. Okay? 2 newspapers reported on this data, USA Today and the Washington Times. USA Today's front page headline was, "Number of 2-parent families up." Okay? The Washington Times headline was, "Traditional families less common." Right? USA Today said, "Number of 2-parent families up." Washington Times said, "Traditional families less common." They both saw the same data. They saw exactly the same data. How could it be? Yeah. Possible, but not what it was. Yeah? But that's always check what the definition is for whatever people are measuring. Yeah, did you have a? Maybe, but not in this case. She was talking about different assumptions. Yeah. Good, okay. We have a distinction here between raw numbers and percentages. Raw numbers and percentages. This is a really important thing to understand. In truth, the number of 2-parent families had risen. Why? The population grew bigger, right? That rose. As a percentage of all families, family types, it actually declined. So both headlines were accurate, but they don't necessarily reflect, well, what do they not reflect? Or what do they reflect? Right? Traditional families less common versus number of 2-parent families up. What is that reflecting? Right? They both have the same data. They both are accurate. Yeah. Yeah, points of view. Okay? When you read something, you should understand, or you should have some idea of the point of view that it's coming from, right? Which is why it's always valuable to read a variety of different things from different places, you know? No matter what your political bent is, it's a good idea to have some idea of what's going on. So I want you to understand this distinction between percentages and raw numbers, okay? All right, good. So with that in mind, what we're going to be talking about now is presentation. When I do a study, right, when anybody does a study, when we do research, and, you know, I emerge from my lab having crunched the numbers and found something really interesting, what do I want to do with that information? Right? All of a sudden, eureka, I found it. What do I want to do with the information? Do I just want to put it in my desk drawer? I think I heard somebody say it. Publish it, right? I want to communicate it. I want to tell everybody, right, about my wonderful research. So what we're going to talk about in this chapter is ways that I present my data so that I communicate what's going on. Now, one rule of thumb you should keep in mind whenever you're doing any of this, whether it's reporting in text, a report, a thesis, any of this, you want to make it easy for people to understand. You don't want to make it hard for whoever's reading your paper to figure out what's going on. You want to make it as easy as possible. So with that in mind, we're going to talk about various ways of presenting your data. Let's look at our first example here. Aaron, Paris, and Aaron in 1995, they gave a stress questionnaire to 151 students. Examples of the questions were things like, how stressed have you been in the last 2.5 weeks on a scale of 0 to 10? 0, not stressed at all. 10, as stressed as possible. Now, aside from the issue of Well, when do they ask this question? Right? Because asking you guys now is a whole lot different from asking you at, let's say, midterms time or finals time or in June. Right? I think you would respond to this differently. But let's say they were trying to get at, this time period. All right, so what do we have here? We would have 151 scores. And if I wanted to find out what was going on, right, I get this data, and I want to go show somebody and say, here, look, this is the data on how stressed students are. And they're going to see 151 points. Is that useful? No, right? That's like useless. You can't see patterns. You can't figure out what's going on. You can't tell just from looking at 151 numbers. Are they stressed? Are they not stressed? What's happening? So what do? Well, there are various simple things to do. First, we're going to talk about putting things in what we call a frequency distribution. And I know a lot of you have done various things like this already, so I may go a little quickly. Slow me down if you want. A frequency distribution. When we talk about distributions, we mean listings of scores. And again, score is generic here. It could be heights, weights, reaction times, IQ scores, whatever. Okay? But it's a listing of these values. Frequency, how often they occur. So a simple frequency distribution, we have our stress ratings 0 to 10. And then I just put how many kids scored whatever. So from looking at this, we can see, most of the kids were scoring an 8 or a 7. So at least you have some idea of what's going on when you see it listed this way. We can make the listing even more useful. Okay? This is called a cumulative frequency distribution, a cumulative frequency distribution. Cumulative because it accumulates the scores going up. For example, let's take a look at how this is created. Here's my simple frequency distribution. How do I get this? Well, I start at the bottom. How many kids got a score of 0? 2 of them. So my cumulative frequency here is 2. How many kids got a score of 1? Well, 1 did. So I add that 1 to my 2, and now I say 3 did. And if I go up to 2, how many got that? 3 of them did. So 3 plus the 3 equals the 6. Now, so what does a cumulative frequency distribution tell me? It tells me the number of people that scored at or below a particular value. The number of people that scored at or below a particular value. It gives you, in essence, a relative location of your score. We're going to be talking about that a lot, locations of scores and distributions. So this is one way to get it, so that I know that for a score of 6, let's say, 65 people scored 6 or lower. So that's helpful. That's helpful. We can take it another step further. By looking at proportions, or even percentages, fractions here. Okay? What do we have here? Look at this. So I have my stress, I have my frequencies, I have my cumulative frequencies. This RF is relative frequency. Relative frequency because what I'm going to do is turn it into a proportion or a fraction. How do I do that? I take my frequency and I divide by the total number of scores in my distribution. I take my frequency and divide by my total number of scores. So, for example, okay, let's say I take a score of 8. 26 people had a score of 8. That's 26 divided by 151 gives me that value. Okay. Now the next column over, cumulative relative frequency is simply cumulative frequency, again, in proportions or fractions. So look up at the top, right? The cumulative frequency at the very top is 151. That's our total number of scores. Why? 151 people scored a 10 or lower. That top number is always going to be n. It's always going to be n. If it's not, it means you did something wrong. Okay? So my cumulative relative frequency is going to be my cumulative frequency divided by n. So again, this gives me the fraction or the proportion of people who scored at or below a particular score. But the one we use most of all is the cumulative percentage. How do I go from a proportion to a percentage? Multiply by 100. So that last column gives me the percentage of people that scored at or below a particular score. All right? Now this is useful, and we'll get to it when we talk about group frequency distributions. But in terms of, again, your location in a distribution, you've been taking standardized test scores probably since you can remember. I don't even know what grade they start them in now. But one of the ways they present the results is the percentage of people that score at or below your score. You know, and then you make mom very proud, right? My little son scored, 90% of the kids scored below him, at or below him. Right? Okay? So it's a very typical thing that's used. So those are ways that we can present our data just by listing it. Now we're going to talk about pictures, right? Graphs. Again, you want to make this as easy as possible. You want somebody, if you have something good you're presenting, you want them to open up the paper and see it like that. Now, before we talk about the graphs like that, I just want to show you a couple of pictures. Let's see how close we can make these, that you can still see what's going on. Okay. Now notice something, all right? These 4 graphs, these are just kind of basic pictures. It's the same data for all those graphs. Let's take a look at these 2 for a minute. Do you see the difference? Right? What's the difference between this one and this one? Yeah. Oh, okay. Sorry. Yeah. Yeah, the scale is different. On the y-axis, the scale is different. I changed it, all right? Both of them they're both showing the same data, but it looks a little different here. Doesn't it look like it's increasing more, right? And look at these guys. Don't they even look steeper, that slope of that line? What about the last graph, this bottom one? What did I do entirely there? You see it? Yeah. Yeah, I totally deleted the information off the y-axis. You may think people don't do this. People do this all the time. All right? Maybe not in professional journals, but in popular media. Because what they want you to see, what your mind grabs automatically, is a steep incline. And you're automatically drawn to, well, what's increasing so much? Okay? And that's just, but they're not showing you the units. Now, which graph would I use? Let's say this is my theoretical income, okay? Really theoretical, okay? And I go, let's say I want to get a raise, right? Which graph am I going to show? The first one, right? Look, I've been working my fingers to the bone for 15 years, but my salary has been essentially flat. Poor me, okay? Whereas, what if I'm going to the bank for a loan? What might I want to show? Well, maybe one of these or one of these, right, that shows I'm a good risk, right? My income has been increasing steadily over 15 years. Now, again, so what I want you to do is pay attention to how things are presented to you. I've worked with people who look at me and say, they ask me to do graphs and stuff like that. I bring it to them, and they look at me and say, can you make it look better? Okay, so keep an eye on what are people telling you. What are the units? Right? Are things labeled properly? And again, this is what you should be doing also. Make sure your stuff is labeled properly. Make sure the units make sense. Okay? It doesn't mean that this is wrong necessarily. I would fix it better to show, like a breakdown here, because it makes it indicate as if that bottom axis is a 0 point, and it's not. But that's sort of what people do. They kind of draw you in to make you think something is not. Okay? So now let's talk about graphs that you're going to be doing and the type of data that you need. And again, I know this is review for most of you. Bar graphs. If you have a discrete variable, remember we made a distinction between a discrete and a continuous variable, right? The kind of pets people have in a family, cats, birds, dogs, fish. That's discrete, right? There are no values between cats and fish. Okay? So you would use a bar graph to indicate that. This example has a relative frequency of family structure types. All right, and so we have that down here. The bars don't touch if it's a discrete variable because you want to indicate that they're separate from each other. And the height of the bar reflects frequency or relative frequency or proportion. By the way, in packages like SPSS, they might not use the word frequency, they might use the word count. Okay? So you would use this for usually nominal level data. You could use it for ordinal, but it depends on what you're doing. Let's take a look at these two types of graphs. The top is a histogram. And the bottom is something called a frequency polygon. Now, in the top one, the histogram. Oh, can't see it, huh? Histogram. A histogram. So in the top one, because stress as a variable is continuous. Do y'all see that? Stress as a variable is continuous. So in a histogram, the bars are touching. In a continuous variable, with a continuous variable, use a histogram, the bars touch to indicate that there is no gap between values. Now, I have to make a distinction here between something we call real limits and apparent limits. Real limits and apparent limits. If you have a continuous variable, then let's take weight, for example. A continuous variable like the weight, and let's say we have 150 pounds. Theoretically, nobody weighs exactly 150 pounds. Remember, we talked about if we use a finer and finer measuring instrument, we get finer and finer gradations. So nobody has exactly 150 pounds. What they have is a tiny little range around 150 pounds. Those are what we call the real limits of the value. And the real limits of the value are half a unit above or below the value you're talking about. So for example, if you're talking about 150 pounds, the real limits of that number are 149.5 to 150.5. Those are the actual real limits. Okay, so let's look back at our histogram for a minute. In a histogram, the bars go from the lower real limit to the upper real limit of the value. So you'll notice here, right? When it starts out with 0, actually, the bar goes from minus 0.5 to positive 0.5. This one goes from positive 0.5 to 1.5. The values are actually over the real limits. Okay? Is there anything more I want to say on a histogram? I don't think so. Okay. And then the bottom, the frequency polygon, all I want to say is that if you put points above the values or the middle of those real limits, right, and you join them with a line, that's a frequency polygon. Okay? It's essentially just joining, connecting the dots, right? It's playing connect the dots down here. The only thing that you might not have is, one thing I did is I drew in the lines from the values above and below the last value, right? Because you have zeros and you have there's a possible value for 0. There was a stress rating of 0 and a stress rating for 10. But there was nothing below 0 or above 10. So often what people do is they draw lines down to the x-axis to indicate that. Okay? Just a little side note. Here's another type of graph. And this is how we graph cumulative frequencies. These are called ogives. Yeah, you can also tell me if you need stuff moved up there because I don't often see behind me. An ogive. And they have that distinctive kind of S-shaped curve. Because remember, cumulative frequency never decreases. Right? It never goes down. The number never goes down. The frequency never goes down. That top number is always n. So you always get that kind of distinct curve shape. Now, what is nice about like on top here is cumulative frequency. On the bottom is cumulative percentage. I just changed the scale. Now, what is useful about this, it would be more useful if the resolution was better. That would be good. Is if I wanted to talk about intermediate values and the cumulative percentage. So all I would have to do is like draw a line. Like let's say I'm interested in a score of 4. I'm interested in a score of 4 and I want to know what is the cumulative percentage. How many people scored at or below a score of 4? And all I have is this graph. So I draw a line to 4. 4 is going to be there. And then I draw a line across. Not as straight as I would like, but. So that's approximately 19%. Now, I want to make a distinction here between what we call percentiles and percentile ranks. Percentiles and percentile ranks. A percentile rank is the percentage of scores that falls at or below a particular value. Percentile rank. So for example, if you got a percentile rank of 80%, that means 80% of the people scored at or below whatever you scored. The word percentile refers to the score. So percentile rank refers to the percentage. Percentile refers to the score. So for example, if I wanted to know, I don't know the numbers on the MCATs, but like if I wanted to know the percentile, let's say I find out that people who score in the bottom 10% of the distribution don't need to apply to med school or something like that. I'm sorry for you pre-meds out there if this raises your anxiety level. But, right, so what I want to know is I want to know the score that reflects that bottom 10%. I don't know what it is. I'm afraid to say it out loud or to make a guess. But, right, so that would be the percentile versus the percentile rank. Okay? So I can get the percentile rank from a graph. I could get it from my cumulative percentage distribution, but I can also get an approximation from the graph. So it's useful that way, these ogives. Yeah? No. The percentile is the score. It's the value. Right? So like if I say that people who score a 70 in this class have a percentile rank of 75. That means 75% of the people fell at or below 70, but 70 is the percentile. Yeah. Yes. So for example, in the stress ratings, I'll get you in a second. In those stress ratings, right, I forget what the numbers were, but let's say a score of 4. We could look back at it. Why don't we do that for a moment, actually? Let's look back at it for a moment. Okay. Right? These would be the ranks. These would be the percentiles. Okay? So, a percentile rank of 22.52, let's say, corresponds to a percentile of 4. Is that good? Did you have a question still, or is that useful? An ogive is just that graph that I had up there that I showed you that has that distinctive S-shaped curve. It's a way of graphing a cumulative frequency distribution or a cumulative percentage distribution. Okay? What else? All right? Okay. Now, that was all fine and dandy when our numbers were simple, right? I only had 10 values. My stress values are only 0 to 10. What if I have more than that? Well, here's the data. What's the background story on this? The background story on this is that some researchers wanted to find out about children's attitudes towards learning and work. So they asked 153 teachers to rate their students' attitudes. So again, one thing I want to point out in this study is they didn't ask the children, they didn't give the children a questionnaire to assess their attitudes. They asked a third party to assess their attitudes. Right? Just keep in mind when you're looking at these things, who's doing the assessing? It's also a useful thing to do. Now, in this study, the scores ranged from 24, which was the most negative a kid could score, to 120, which was the most positive attitude they could score. Okay? So here we have the numbers. All right? So what we have here is we can't list 24 to 120 and then put the frequencies next to it. That would be a simple frequency distribution. Not useful here. There are too many values. And some of those values might be 0. It's not an efficient way of listing what's going on. So what we do is we create a grouped frequency distribution. Now, just as a side note, like the graphs I'm showing you and things like that today, these are all actual data that's being plotted. What we want to move forward in statistics is to move forward from actual graphs to theoretical distributions that are smoother, that give us some more information on the data that we're talking about. So we're going to wind up using theoretical distributions, especially when it comes to probability, as opposed to just the numbers that we have. And you notice, right, everything is kind of spiky. The more values that you have, right, the larger the number of scores you have, the smoother that distribution is going to get. Until it gets, for all intents and purposes, like an infinite distribution, looks perfectly smooth. So let's talk about our grouped frequency distribution and how we create this grouped frequency distribution. You've all seen this, right? It's like, okay, I can't do 24, 25, 26, 27. That doesn't make any sense, so I'm going to put it in groups. And by the way, you can use the word group, interval, classes. They're all kind of used interchangeably. So what we have here, this is my grouped frequency distribution. How do I get that? Well, first off, what I might do is think about how big do I want my interval to be? My interval width, or my class width. How wide do I want it to be? Now, you can make it be however you want. In this, though, you want to think about what's the best way to present things. Right? What is going to make it clear? Why do we have it in these numbers now? Well, think about what makes it easy for us to understand. We like seeing things in 5s and 10s, you know? So you might want to go in that way. You don't have to. But again, you're just going for ease of presentation. All right, so here, what is my interval width? It's actually 10. It's actually 10. Why? Because it's my real limits. It's the difference between my real limits. These attitude scores, is it a discrete or a continuous variable? Attitude. Continuous. Continuous. Yeah? Again, make sure you understand the distinction between the variable and the level of measurement. Right? The measurement, yeah, they gave you points. Right? The variable itself is continuous because there are all sorts of infinite gradations of attitude people have. Okay? So, therefore, we need the real limits. So the real limits, like to get this bottom value, is 19.5 to 29.5. So that interval width is 10. When we write it down, we write it, these are called the apparent limits. The apparent limits. So we write it with the apparent limits, but we calculate it with the real limits. So our interval width is 10. Now, you have to set it up so that your intervals don't overlap. There are no gaps between the intervals, right? And so how do we do this? Well, first of all, we now have to figure out how many intervals we need. How many intervals we need? Yeah, you have a question?
Yeah, just so the values that on the questionnaire are discrete, but the scale is continuous. Is that what you're saying?
Well, don't say it that way. Don't say the scale is continuous. It's not that the scale is continuous. The scale wasn't continuous. The variable was continuous. Yeah. It's 19.5 to 29.5. Okay? Okay? So, what we have to do, we have to determine how many intervals. Now, everybody always asks me, well, how many intervals should there be? This is where it's a little more of an art than a science, okay? Often, people will say somewhere between 10 to 20 intervals is good. That's pretty wide, and it also depends on the data that you're displaying, okay? Let's take a look. The first thing that you should do is find the range of values. Now, how do I find the range of values? The range of values is the highest number minus the lowest number. Possible in your scores. Okay? Again, using real limits. So in this case, what would it be? 120.5 minus 23.5. Right? I said that the lowest possible score a kid could get was 24, and the highest he could get was 120. Sure. Okay? So that's how big my range is. Yeah? No, the possible values you could get. I gave this when I started talking about it. A kid could only score up to 120. Hold the question. I know what your question is. Hang on to it for a second. Okay? I know what you're going to ask. All right? So that's the range of values that I have in my data. Now, how do I determine how many intervals I'm going to have? I divide this by my interval width. I divide it by my interval width. So I should have 9.7 intervals. Now, am I going to have 9.7 intervals? No, what would I do? Round it to 10, right? Round it to 10. Do I have 10 intervals there? Count it. How many do I have? 11. You start at the bottom and you work your way up. Now, could I have started with 24? Yeah, I totally could have started with 24. But is that the way you generally see data listed? Right? 24 to 33, 34 to 43, 44 to 53. Is that how you would expect to see the data listed? Not so much. Not so much. Would it be wrong? No. But it's not typical. So we start with, and usually you might start with a value that is a multiple of your interval width. Okay? So we start with 20, and if we start with 20, working up all the way to from the bottom to the top, we actually wind up with 11 intervals, not 10, or 9.7 for that matter. But this is just to make it clear. Now, your question essentially was, why do we have an entire interval for 120 to 129 if the kid could only score up to 120, right? Isn't that sort of what your question is? Yeah, normally what you would do is in your text you would write what the values of scores were, but you would still present it this way. Because it's consistency, right? It's consistency. We don't have, 10 of our values look one way and then the last one looks different. The value is putting it in a consistent fashion. So that there's only that one score in that entire interval. Yeah?
So are you saying then that way, is that the best for the so out of anything that we do, it's better to have something that's consistent than
You mean more accurate?
yeah.
No, because it's not inaccurate. It's not inaccurate. And here's one of the problems, by the way, with a grouped frequency distribution, right? And this goes to what you're both talking about. You lose information, right? You lose information about individual scores when you present data this way. But what I would argue is that in the paper itself, if you were writing this up, you would make it very explicit that a child could not get over 120. But you would still present the data like this. Because otherwise what would happen is it would look unprofessional, right? Because you would have 10 intervals looking one way, and then that top interval, you would just have like a 120 and a 1 next to it. First of all, you would have to play around in the computer packages to get it to do it customized the way you want it to. But it would just look like you don't know how to do it. Okay? Yeah? 23.5 is the lower real limit for a score of 24. Right? It's half a unit below 24. And 24 is the lowest score a kid could get. Okay? Okay? All right. So that's essentially how we get our grouped frequency distribution. And you could do the same thing as we did with the simple frequency distributions, right? We have the cumulative frequency, we have the relative frequency, and the cumulative relative frequency. And they're all doing the same thing. And again, right, this is the problem you were talking about. You had 30 kids scoring between 110 and 119. You don't know what those values are. You don't know if all those kids scored a 110. You don't know if they scored, right? You have no idea how it's distributed throughout that interval. But you could, if you wanted to, still find percentile ranks using this information. Now, let's put that back for a second, right? What could I do if I wanted to find the percentile rank? What's the only column missing here? Yeah, over here, just multiplying everything by 100. Now, the problem is, if I had a value for, let's say, I wanted to know what the percentile rank is for 119, that's fine because it's at the top of the limit, right? It's at the top of that interval. So everything here and below would be categorized, that would be the percentile rank for that value. But what if the value I was interested in was 112? How would I find the percentile rank there? Does anybody know there's a term, actually, what you would have to do? Yeah. Yeah. Interpolation. Interpolation. You would have to interpolate to figure out exactly what the percentile rank was from a grouped frequency distribution. Here's my present to you today. We are not going to do interpolation. Okay? It's in the book. You want me to go through it with you? No problems. But we're not going to do it. Because for one thing, we don't do this stuff very often anymore. But the bigger problem is what I was alluding to before. Linear interpolation implies that all the values are evenly spaced over that interval, which is not necessarily true, right? It could be that all the kids scored, right? Like if we look at this one again, it could be that all the kids scored 118. But if I interpolate that, I'm assuming that those 30 scores are spread evenly over the interval. So we're not going to use it, okay? Graphing a grouped frequency distribution. Here are our teachers' ratings. And again, here's our histogram. Notice our real limits down here. All right. And up here, here's our frequency polygon. And again, the only thing I did was I extended it. I extended it down to the x-axis. Okay, so you could use, like, you could use a frequency polygon. You could use a histogram. Yeah. Yeah. Yeah, it was probably an issue that I had with SPSS or Excel. Okay. Yeah, ideally. Sometimes people like eliminate some stuff if it's too cramped on the bottom, or they do it in different ways. But okay. So those are the typical ways that people graph things. However, I'm going to show you one more graph that's very interesting and very useful. It's called a stem and leaf display, or a stem plot. Okay, and that's here. Now, what was the problem with a grouped frequency distribution? What did I say was the major problem with a grouped frequency distribution? Yeah. Right, right. I lose information about individual scores, right? That's what happens. I just lose all that individual score information. Here is a very nifty way of getting it back, okay? Notice all the values on this side, all the numbers on the right-hand side, those are called the leaves. The values on this side are called the stems. The leaf is the last digit of whatever your value is. The leaf is the last digit of whatever your value is. The stem are all the numbers in front of that last digit. So let's take a look at this for a moment. Okay? Look at the first one, a 2 and a 5. What that means is that there was one kid who scored a 25. Right? Because there's 1 5 here, that 2 represents 20. If we go to 3 here, this means that one kid scored a 30 and one kid scored a 32. In the 4 column, or the 4 row rather, we have one kid scored a 40, one kid scored a 42, one kid scored a 43, one kid scored a 44, and there are 2 45s. There are 2 45s. So do you see what this is? We get to keep every single individual score right there. No data are lost. And you flip it this way, you still get a basic idea of the shape of the distribution as well. So you get all the information that you get better than with a histogram. So these are becoming increasingly well known, especially in what people call exploratory data analysis, EDA. Do you guys have a question? Do you need help with something? Okay. So exploratory data analysis, EDA, is, I'm not going to say it's its own discipline, but one of the things that people need to do is you get numbers. right? You collect your data. And then what you have, everybody's first inclination is to crunch the numbers to see if they got what they think they're going to get. But there's a whole lot more to looking at the numbers than just seeing what the average is or anything else, And exploratory data analysis, one of the things we do is graph your data. Look at your data. Because you want to know certain things like, what's the shape of your data? Do you have any extreme scores? What's an extreme score called? Yeah, outliers. Outliers, right? Because all of those things could be an indication of what's going on in your data that could mess you up. Something stupid. You're typing in data, and people make typos, right? So let's say I'm putting in class scores, and for 2 people, I put in 800s instead of 80s. And then I find the class average. Of course, it's going to be wrong. But if I graph everything first, I can see, oh, yeah, that was a stupid thing I did, and I'll go back and fix it before I take it further. Okay, so stem and leaf displays or stem plots are useful for things like that. You can see the outliers. You can see the individual scores set up. It's good. What can you do with this stem plot? There's a couple other things you can do. One thing you can do is you can make the scale more refined. Here, these are in 10s, right? You could do it in 5s. You could do it in 5s and make it even more refined, right? So instead of having 1, 2 here and 1, 3 here, you would have 2 2s. 20 to 24, 25 to 29, 30 to 34, 30 to 39, all right? And that would just make it a more finer gradations. Another thing you can do is, let's say, this is from one particular school district. What if I wanted to look at another school district? Well, you know what I could do? I could just plot it on this side. So I could see the 2 of them right next to each other. Okay? So those are nice. They're very, very useful. Okay? Questions on that? Questions on the stem plot? All right, so there's one last thing I want to show you. And this is a graph that I got from the Times last year at some point. Where can we move this? Okay. And what it's a graph of is retail sales of garments comparing the Chinese market and the United States market. Their point in the article was that even though America, the United States, had a larger share, China was increasing much more quickly. Now, what are my issues with this graph? Well, there's a couple of different things. First of all, look at the x-axis. Anybody see a problem with that? I don't know if you can tell. Which numbers on the x-axis? These are years of sales, the years of the sales. So 1990, right? This would be 1990. This would be 2002. This is the Chinese market. This is the United States market. This one is the Chinese market. This is the United States market. Yeah, right? They're comparing different years, right? The Chinese market, they're showing 1990 to 2005. And the United States, they're showing, 2002 to 2005. So they're not comparing the same things. That's not a good idea. Now, one of the ways that they think that they tried to fix it is, I don't know if you can see, it's kind of faint on there, these gray boxes around it. Not so useful. They should either present all 15 years for both or just 3 years for both, right? That's not helpful. What about the y-axis? You know what's annoying to me about that y-axis? The numbers are above the lines. Why not just make this line, cut it in half, and put the number next to the line? There's an idea, right, for clarity. Right? They don't have the 0 point. It would kind of make you think that that's 0, but it's not. Down here is 0. And the last thing that really defeats the purpose of the graph is notice these last bars for 2005. For 2005, they only had data for the first 6 months of the year. Now, what they're trying to show is that the Chinese market is growing much faster. If it goes down like that, do you think it really gives an indication of increased growth? Yeah, maybe not, eh? So it's like I said, this is just like an example of where you run into problems. Just leave them off. Just leave off those, the 2005 for both groups or something. Probably would have been much clearer, better understanding of this. Okay, yeah.
So they didn't have data from the United States or greater.
Of course they did. They just didn't present it. Yeah. All right? All right, I'll see you guys Wednesday.